Euclid's Elements, Book 3, Prop 1. To find the center of a given circle. So this is a simple construction proof. So we have a given circle. We'll call this circle ABC. And we just want to find the center of this circle. So the first thing we're just going to do is we're going to take any line at random here. So we're going to create a chord. So we're just going to connect any two parts of the circle with a straight line. So we're going to make AB. And we can bisect any given line. So we're going to then bisect AB. And we can do that with proposition 10 of book 1. We can bisect any line into 2 equal halves. So we're going to bisect this line at point D. And at point D, so this is going to make AD equal to DB. And at point D, we can draw a line perpendicular to a given line. So at point D, we can draw a line DC perpendicular to AB. So we'll make CD perpendicular to AB, and we can do that with book 1, proposition 11. Now let's extend CD until it intersects the circle at E. Can extend any straight lines. And now we can take and we can bisect CE. Again, using book 1, prop 10. So if we bisect CE, let's call this point F. So we have FE equal to CE, and we're going to say that we have achieved our goal, that F is the center. I say F is the center of our circle. Now, the proof of this is going to be a proof by contradiction. So we're going to say, well, let's assume for the moment that that's not true. If F is not the center, then let G be the center. So let's pick another point G, and have G be the center of the circle. If it's the center, then we can connect GA, and we can connect GB, and since this is the center, these are radii of the same circle, therefore they're equal. And we can connect point here, we can connect GD. And what we can see here is we have 2 triangles, and they each have one side equal to one side, another side equal to another side, and they have this third side in common. So we can see that they have all 3 sides in common. So this reminds us of prop 8, which is our side-side-side theorem, and it proves that these 2 triangles, any 2 sides contain an equal angle. And so we can show that this is through proposition 10, or definition 10. Definition 10 says that when a line falls on 2 lines making the angles equal, and these are equal because of, so here, let's just do this, angle ADG is equal to angle BDG. And because those 2 are equal, then both of these angles must be right angles. That's what definition 10 tells us. But, so let's redraw this. We'll say that this one here is a right angle. Both of them are right, but we'll just focus on this one here. So this is a right angle. Well, what's the problem with that? Well, the problem is we already know that this is a right angle. We know that angle FDB is a right angle, because we built this as perpendicular to AB. And we should notice that the angle in green is only a part of the angle in black. So this would be the whole angle, and this is just a portion. And we know from common notion 5 that the whole is greater than the part. And since this is the whole, this must be greater than angle GDB, or what we're calling it BDG. But if this is a right angle and this is a right angle, they're also equal. So this angle is both equal to this angle and greater than it. Or the angle that is lesser is also equal to the greater. And that is absurd. So we have to get rid of whatever created that absurdity, and that was what created this absurdity is assuming that F is not the center. And the same absurdity occurs no matter where we put our supposed center, unless we put it right here on F. So any other line that is in F will create this absurdity, therefore F must be the center. So F is in fact the center of our circle, and that's what we were supposed to do. Now there's a porism that goes along with this. It's just something that's immediately evident, and that is if you have a straight line and another straight line bisect that line at right angles, then the center of the circle is going to be on that cutting line. And so it is. The center of the circle is on the cutting line CE. Since that's our construction, we conclude QEF.